As electricians, we're all taught the same thing. Higher voltage equals higher danger. It just makes intuitive sense, right? But what if I told you that when it comes to arc flash, that intuition is dead wrong? The actual physics of incident energy tell a completely different story. And frankly, it's a much more lethal one. So let's break down the engineering behind this crazy paradox.
So I'm going to ask you a straight question. To every master electrician, every safety manager, every facility engineer watching right now, look at these two scenarios. Based on everything you know, which one poses the greater threat for a life-ending burn?
On your left, you've got this absolute beast of medium voltage switchgear, 13.8 kV. And on the right, a standard 480-volt panel board, the kind you'll find in basically any facility in the country. Now, your gut is screaming high voltage, but the real answer has nothing to do with voltage. It all comes down to two simple variables. And trust me, understanding them is the difference between a worker going home and a catastrophic failure.
Okay, before we get into the real nuts and bolts of the engineering here, do yourself a favor and hit that subscribe button. We drop advanced, actionable safety modules just like this one every single week, and you are not going to want to miss out.
All right, so the heart of this whole thing isn't the voltage, it's the incident energy. That's the real measure of the hazard, right? It's the thermal energy, measured in calories, that's going to hit your body. And that energy is really governed by two key variables that are, frankly, dangerously misunderstood, especially in low-voltage work: distance and time.
So let's talk about variable number one, working distance. NFPA 70E gives us the official definition, but it all comes down to the inverse square law. It's just physics. Simply put, the energy of that blast dissipates exponentially the further you get from it. Doubling your distance doesn't cut the energy in half. It cuts it down to a quarter. In an arc flash event, distance is your absolute best friend.
And this slide just drives that point home. It's what we call the proximity multiplier effect. The worker on the left, dealing with 13.8 kV, is using a hot stick. He's keeping himself 4, maybe 5 feet away from the danger. But look at the electrician on the right, troubleshooting that 480-volt panel. He's right up in it, maybe 18 inches away, just arm's length. That proximity alone multiplies his energy exposure through the roof. And we haven't even gotten to the second variable yet.
Okay, variable number two. And honestly, this is the one that's far more dangerous and far more misunderstood. It's the clearing time. We're talking about the duration of the arc flash itself. How long does it take for that upstream breaker or fuse to finally do its job and kill the circuit? This is where the paradox really becomes a killer.
The data on this table tells the whole story. Your medium voltage switchgear is engineered with some pretty sophisticated relays. They're designed to clear a fault in half a second, maybe less. But now look at the low voltage gear, the panel boards, the motor control centers. Their protective devices can take a staggering 2 seconds, or sometimes even longer, to trip. So why the massive delay?
Well, that delay leads us right to something called the arcing current trap. This is an incredibly dangerous phenomenon, where a standard, everyday, low-voltage breaker completely misinterprets a deadly arc flash and thinks it's just a normal day at the office.
So here's the engineering. An arc has to jump through open air, right? And that air gap acts as a resistor, which can drop the fault current just enough so that it doesn't hit the breaker's instantaneous trip setting. So instead of tripping in milliseconds like it should, the fault gets pushed onto the breaker's time delay curve. That curve is designed to let big motors start up without causing a nuisance trip. The breaker thinks, oh, must be a motor starting, and it just waits. And for those critical seconds, that worker is being cooked.
And this dangerously long clearing time leads directly to the single biggest, most dangerous myth in all of arc flash analysis, the infamous 2-second rule. So many engineers, so many electricians believe that an arc physically cannot last longer than 2 seconds, and that belief comes from a complete misunderstanding of the standard, a misunderstanding that has fatal consequences.
Here it is, straight out of the IEEE 1584 standard, but you have to read it carefully. This isn't about the physics of an arc. It's an assumption about human behavior. It says it's likely a person will move away. It's a guess that a worker will have a fight or flight response and get out of there. And the most important phrase in the whole standard is right there at the end, if it is physically possible.
So let's be absolutely crystal clear. The 2-second rule is an assumption about a person's reaction time. It is not a physical law that limits how long an arc can burn. It is not a guarantee that you're safe, and it absolutely is not something that should be applied automatically to every calculation. The arc doesn't care about a 2-second assumption. It's going to burn as long as that breaker lets it. So what happens when that core assumption that a worker can actually escape is false? What happens when it's not physically possible? The consequences are catastrophic because the calculation that was used to pick out their PPE was based on a complete fantasy.
And let's be honest, these scenarios are everywhere. A lineman working out of a bucket truck. Where is he going to go? An electrician squeezed into a narrow electrical closet with his back against the wall. A technician kneeling down inside a vault. In these confined spaces, there is no escape path. Moving away is not physically possible. And applying that 2-second cap in the hazard calculation, well, that's just professionally negligent.
This isn't just a theory, this is reality. We have documented case studies where, based on the breaker's actual time current curve, the clearing time was nearly 24 seconds. The true incident energy? 170 calories per centimeter squared. There is no PPE on the market that will save you from a 170-calorie event. It is simply unsurvivable.
But if an engineer incorrectly applied that 2-second rule, the label on that same piece of equipment would read 14.4 calories. So your electrician suits up in 20-cal gear thinking he's protected. He thinks he's safe, but he's not facing a 14-calorie hazard. He's facing a 170-calorie inferno. This right here, this is how fatalities happen.
So this brings us to your mandate. Your responsibility as a safety professional, as an engineer, as a site leader. You have to go back and you have to critically reevaluate your arc flash hazard analysis, and you have to hunt for this specific dangerous assumption. And here's your 5-step action plan. Step 1. Pull your studies and find every single label where the incident energy was capped at 2 seconds. And you might have to dig for it. It's often a buried setting in the software. Step 2. For every single one of those tasks, validate the assumption. Is escape really possible? Be brutally honest. Step 3. Scrutinize those time current curves. Look for those low-level arcing faults that fall into that long, slow-cook delay region. That's the heart of the problem. Step 4. If escape is not possible, you must recalculate using the full uncapped clearing time from the device. And finally, Step 5, the most important one. Relabel the equipment and update your PPE requirements and your procedures to reflect the true calculated hazard.
Getting this level of detail right is absolutely critical. It's how we make sure our people go home at the end of the day. Make sure you subscribe because you won't want to miss our next explainer where we are breaking down advanced lockout tagout for complex machinery. Stay sharp out there and stay safe.